Hello, everyone. Welcome to the chapter 9 of the AI Engineering Bootcamp. And this week, we have welcomed Mir, who did the presentation before, and glad to have him back and giving us a summary of this chapter on inference optimization. Take it away, Mir.
Yeah, thank you, Lou. So this week we'll be talking about inference optimization of chapter 9. In this chapter, we'll be talking about how we can optimize transformer-based language models for inferencing. So let's go ahead. So first, during inferencing, the main aspects which we'll be having is two things, that is prefill and decode. Well, the pre-fill part is where we'll have our own prompts and input tokens, which need to pass through the transformer language models. And since it's a recursive model, it has to compute all the attention caches before generating the next token. So that will be a prefill, and that will be a compound compute bound because there we already have all the input text available, and we have to compute all the caches and intermediate steps for that. In decode stages, where that is when the model starts generating output tokens, and those are usually memory bandwidth bound because uh, it has to generate each token at the time, and that will take a lot of bandwidth in the GPUs. And usually in production, both the stages are decoupled because of their different needs, and because based on that, the optimizations are carried out. Next, first we'll try to understand what are the computational bottlenecks. One thing is compute bound, where the processing is limited by the processing power. Like example is decryption. And second aspect is memory bandwidth bound, where the data is not able to transfer itself towards the compute. We have very much high compute, but the data is not able to be is bit slower with compared to the computation. And this means that we are bounded by the memory bandwidth and not by the compute. And usually we determine our inference steps, determining based on the bottlenecks, just as we had discussed before. For prefill, it is usually compute bound, and for decode, it is memory bandwidth bound. And there are two kinds of usually APIs which are available in the market. One is online APIs where the latency is very less. It is available. These are things which are available in almost all the API providers. And another APIs are for batch, where we can have multiple data sets and we can ask it to be processed for our inferencing. The ideal use case for batches will be where we need to generate synthetic data. If we have to generate reports, onboarding, we have to migrate from one model to another model for recommendations and reindexing. This is where, based on our use case, situation, and requirement, we can choose between online and batch APIs. Using batch APIs can give us significant cost reduction, which is very much helpful for based on the use case. It will be very helpful for the clients and even the inference providers. Uh, Next, we'll be talking about few important metrics based on which we can decide what kind of computation, whether how much optimization has been provided using our techniques. Well, first metrics which is being used is for time to first token. This means that once we give our input tokens to the model, with that, the amount of time it takes to decode the first token is called TTFT, that is time to first token. And next is TPOT, that is time to per output token. So we start calculating the time for each token which we have been receiving from the model. So the total latency which we compute is adding time to first token and time to output token. And most of the time, you can even calculate it based on percentile latencies. This is a very easy, better metrics, statistical metric, where we can understand how many tokens are based on your requirement, which one is coming under your 90 percentile, 95 percentile, and 99 percentile. Next, there are few more metrics which are good to be used in production, where tokens per second, which is very common metric. Second thing is request per minute, because each and every generating every token might take few seconds based on hardware requirements and input and batching. So we can collaborate more and use requests per minute, which how many requests have been coming per minute to generate the tokens. Second thing, a few metrics which are being used is good put. That means like how many requests out of 100%, how much percent of the requests are meeting our SLAs. And based on that, even efficiency, we need efficiency. We can't just go ahead with higher metrics, but have very high cost. So low cost with high utilization. So that is efficiency, what we have talked in the chapter. A few utilization metrics is model flops utilization, considering like 0 to 100, like 100 is the max flops our GPU or the compute can provide. How much percentage of flops we can use is MFU, and a few others are model bandwidth utilization. Each system has its own maximum bandwidth, which we can be used. So how we utilize these both metrics, and you utilize 100 max amount of hardware utilization is being used on this. There has been some talks where how at the starting people used to understand maximum utilization based on NVIDIA SMIs, where it used to show how much percentage of the GPU we are being used and based on the power consumptions. But later they start explaining how we can use multiple tools like if you're using PyTorch models, you can go ahead with PyTorch profilers. Some are NVProf, NVIDIA profilers, and other vendors based on which we can understand how much flops we are utilizing and how much bandwidth and other metrics. And one thing to note is always high utilization doesn't mean it provides enough latency and cost consumption. Sec In a short part where we talk about AI accelerators, for where the chips have been developed in such a way that we can maximize the computation load. So there are few specialized chips. This is a diagram which I architecture diagram of small diagram of A100 GPUs, where we see that global memory is 40 GB. Next, which is more closer towards streaming multiprocessors, is 40 MB. These are way faster compared to global memory. And then we have L1 caches, that was shared memory, and then there are read-only memories. Then there are registers. So as we go ahead, the speed at which the CPU can access the memories increases drastically. But the memories it can hold is quite lesser comparatively. So how we utilize this pyramid to bring the maximum efficiency is what inference optimization can be used for. Here, there are a few things, key specifications, what we can go ahead with respect to the AI accelerators. One is compute power. How much power do we need to utilize this to its max percentage? How much memory size it provides, and how much bandwidth can it provide? The speed at which it can be accessed, and then on-chip SRAM. That is on-chip. How much memory can we store, and power consumptions. Uh, Now, let's get into the main part where model optimization techniques. The simplest thing, if you have a huge model to be able to run, is compression. If you can compress it, there are mainly three things, famous things where you can see is model distillation. If people know, like, if you know that Hugging Face used to train a lot of distillation models, and with almost very close performance with large bird models during its starting days. Then model prone distillation is where you have a huge large model, and based on its output, we start training the student model. So this is a teacher-student model relationship kind of aspect. And model pruning, where we try to figure out um, which all parameters or which all connections are not being used, and we try to remove it. This is for this, we need to understand the model quite a lot and understand how it works and where all we can prune them such that the model is we can such that the model performance has not been degraded. Another very common and very quite famous is weight-only quantization, where considering like FP16 full precision is being used, and we convert it into a low precision. Right now, we have FP8, FP4 coming up. So these are the three quite famous talk in the book about the model compression. Next, before we go ahead on how we start optimizing, let's just see the understand a basic simple architecture, just like a recap, where we have embedding, positional embedding, and we have a lot of multi-heads. This is a decoder only side of the attention mechanism from Vaswani paper, where this multi-head attention, this for cross attention, this we can skip it. We have feed forward and multi-head attention. Now, if we know about this, since we have talked before, this can go into quadratics. So as the context learn increases, the computation also can increase. So first, how do we understand the decoding bottleneck session? That means because every time we keep decoding one token at a time, not multiple tokens. Based on that, again, excuse me, excuse me. Based on that, we predict another next tokens. The first one is speculative decoding, where we have a main target model, which is quite huge. Our main model, and we have a draft model, which is smaller and takes less compute and generates the tokens faster. And that's called a draft model. And that drafts, as shown as we see in the example, it starts generating the tokens output. And here we can specify how many tokens it needs to generate at the time. Where here we can see 1, 2, 3, like 5 to 6 or 10, based on how much similar they are in generation. And using that, the target model will try to verify whether those outputs are correct or not. Why this works is because this is a generation part where it's decoding, but here when it is trying to verify it, it becomes a pre-fill kind of stage, because you don't generate it one at a time, but you have received so many tokens and you try to see whether it's right or not. So this one becomes compute bound rather than a memory bound. This way, this is a famous. I have copied this from a blog post from Google, where we try to. They show like how using a draft model it becomes quite fast, and this is quite a lot. It has been used quite a lot in inferencing. Next, another technique is inference with reference, where it's a common thing where a lot of the generated tokens might come from our input tokens. So this is what they say is that it's a driven draft, where we'll have cached assistance, where we'll say that now consider knowledge retrievals and things, where we try to ask some questions and give context. Those ways we will reuse the context in the decoding part. So using that, it tries to speed up our decoding stage. Next is parallel decoding. This is where the multiple sequences are trying to be we generate at a time. This is a Medusa heads, uh, where showing as shown as an example, where we will pass through multiple heads which are being trained, and LLM head passes. So this will have sequence 1, sequence 2, sequence 3 will be generated with multiple K tokens. And we'll use another few techniques where it'll try to find coherence and matching accordingly and figure out which one is the right model, which one is the right output, and it'll give it the prediction. This is becomes little post optimization and post processing becomes quite tricky, and still like this is also quite a good usage, where with one inference we can get multiple outputs. Next, we will have once this decoding part is done, next the optimization part. What we talk about is about attention optimization. The reason is here we talk about how attention mechanism is a quadratic computation step where, as shown here, like for every query which we go ahead, we will start piling up as the sequence starts increasing. So here, what I'm trying to say, we are trying to say is like to generate the t token, we will need key and value vectors for 1 to t minus 1. That is from step 1 to time t minus 1. And to generate t plus 1, we might need all the tokens from x1 to xt. That is, we will need it needs to be stored or regenerated. So the first thing is we'll have to redesign the attention mechanism. There are few steps, few techniques. There is one is local window attention. This is where the attention is fixed to only it attends to only fixed size windows of nearby tokens. And second, another two technique is cross-layer attention and multi-query attention. If uh, Here in cross-layer attention, we have seen in encoder-decoder part where during decoder we have a cross-layer attention from encoder to decoder. And second thing is multi-query attention. This is where we are trying to reduce the memory footprint, but there'll be I'll show here. So this is the multi-query attention where the key and value pair are connected with multiple queries. Now, yeah. And this cross-layer attention shares key and value vectors across adjacent layers, and multi-query shares key and vectors across query heads, multiple query heads. And one more thing is group query attention, which is quite famous, where instead of going one key and one value for multiple queries, we start grouping them, and they'll be responsible for only few queries, like here shown in the example. One thing in a use case, what we have talked is about character AI, where they say that they had a primary bottleneck of inference throughput is was the KV cache because they implemented three attention mechanism. One is multi-query attention, interleaving local attention, and global attention, and cross-layer attention. This helped them reduce the KV cache by 20 times. This means that if consider that the KV cache of because of the chatting and multi-chat systems, if KV cache has increased to 20 GB, it has reduced them by 20 times. That means it becomes 1 GB, and this can be stored or transferred. This helps a lot in speeding up the inferences. And because of this addiction, that means that memory is no longer a bottleneck, and then we can utilize the maximum compute. Next, after this, we'll start optimizing the cache. That is page attention, where optimize where the page attention optimizes memory. This is more about memory management, where we can start. We don't need the more data to be in continuous blocks because in usually KV caches need to be continuous blocks so that the compute can be used to the maximum amount and in parallel processing. And because of this, the fragmentation has been reduced, and we can start re-enabling flexible memory sharing and LLM inferencing. Another techniques are KV cache quantization, where the KV caches have been quantized to respective lower precision outputs, and we can quantize, dequantize whenever needed. Another thing is KV cache compression. Depending on the use cases, the caches are compressed and decompressed whenever needed. And selective KV cache, selectively KV caches have been saved, and other might be will be needed to recompute it. This will reduce the time and depending on the use cases. And another aspect of speeding up the inference is writing kernels for attention computation, where the best example we can talk about is flash attention. When the author during his dissertation, he came up and he read, he saw that we are reading lot of memory from the main memory, and he's like, the flash attention is all about like how utilizing the memory hierarchy to its maximum and reducing read and write to the main memory. So here, this is the outer loop. He talks about this is the diagram showcasing how the flash attention works. And in this, one more thing, what they have worked the most about is Usually, if you try to write in PyTorch, one thing, it'll try to run matmul first, then it'll run mask over that. Once we return the output, again we run softmax over that output, then we run dropout. So these are the multiple kernels. Kernels are the low-level code which is used to run on the GPUs. Now, in attention, what they have talked about is flash attention fuses all this operation into one kernel, so you don't have to keep calling again and again. There are multiple overheads, and you'll have to store them in memory, so read and write increases. So because of this fusing, this increases the speed. The read and write has been used only once, so this speed ups your attention mechanism quite a lot. So this was the idea of flash attention, and it's being used, and it helped in increasing the sequence length has become higher. Next, kernels. It's a special. Since I talked about a few things, talked about kernels in the flash attention. Kernels are nothing but specialized piece of code which are optimized for specific hardware. You can talk about GPU, TPU, or even yeah, these are the main things right now. And there are multiple kernels. One is CUDA, which is for NVIDIA. Triton is a generalized framework, which can be used to run on multiple you specific hardwares. We can use Triton to write on NVIDIA GPUs, CPUs, and even I think and even AMD GPUs. And ours, I hope I'm right. It's ROCm or ROCm, which is kernels which are used to write on AMD GPUs. There are a few common techniques which are used while writing kernels. One is vectorization. Vectorization is as shown in the example where we'll have a vectors, and at a time the whole vector is being used. CPUs and even a few GPUs maybe. Like you can utilize flag headers or few flags to run vectors over that. This will be very specialized, and it will process it way faster. Parallelization is where we'll have multiple inputs. We will break them into multiple threads, and we will run them in parallel. Loop tiling is a method where we utilize SRAMs and you can say caches to read and process at a time by rereading and speeding them up. Operator fusion is what we have talked about in flash extension, where multiple operations are fused inside one kernel so that we don't have to keep rereading and writing into the DRAMs. This helps in making it faster. Next, few compilers. This we talk about. There are a few. It is nothing but which tries to lower the code to run on the specific hardware. There are a few standalone compilers, that is Apache TVM and MLIR, and few of integrated into few compilers which are integrated into our famous Python frameworks. Torch compiled, XLAs, and TensorRT compilers. TensorRT compilers is very much used during inferencing by NVIDIA. And next, we'll be talking about inference service optimization, where first thing will be batching. While inferencing, the main thing is like how can we batch multiple requests such that we can use our GPUs to its maximum. So first technique is static batching, which is very simple, where we'll keep waiting until in the inputs are batched together for a fixed amount, and then we'll process it. Uh, Doing that means that there might be a chance that there'll be a huge lag, or there might be a chance that the last request which is needed to fulfill the category, fulfill the number might not come up, and everyone will have to keep waiting until it fills. So next one is dynamic batching. To prevent that, that is like we'll set a maximum time window, and until then, if we can fill it, we will run it. If we don't fill it, then we will go ahead with how much ever size of the batch we have provided. These are good. Next is another one which is being used as continuous batching, where we'll have a specific size of our batch, and we'll keep allowing the request to come in. As the request has been completed, we will return it, and we will uh, take the request which is in the pipeline and keep processing it. This is a continuous batching, and a lot of people use it, which will be helpful in utilizing the GPUs to its maximum. Next is decoupling prefill and decode. This is quite common where whenever an input has been provided, the prefilling is more compute bound. So it will be used on different GPUs, and then decoding will be used with different GPUs. And another technique is prompt caching. Considering like we had talked about in prompt engineering chapter, where there'll be system prompt, usually which will be very common, and it'll be easier to cache them and run it. That way, using this caches, it'll be very faster to optimize and uh, provide faster inferencing. And this is an image from DeepSeek API where they introduce about context caching on disk, where they know that once the system caches and multiple caches start up, that is something which is very much used. And if since it's cached, the inferencing and the speed becomes faster. Now we'll be going ahead with parallelism strategies, where how we can deploy and utilize the parallelism across multiple GPUs to optimize and make our model runs faster. One is replica model, where we will duplicate model into multiple GPUs, and we will chunk the inputs and run it through the models, and then we will get the inputs out. Now, example is PyTorch DDP, distributed data parallel. This means that we'll be running multiple copies of the same model across different devices, and each copy processes a different part of the data. This is a replica model. Next will be tensor parallelism, uh, where instead of giving each GPU a full layer, what we do is we divide the layer into multiple GPUs. This way, everyone will work together, and then they are communicated, and we get a whole piece of information. This is very helpful where if considering very large language models where even one layer cannot be saved in one GPUs, this way we can parallelize tensors and we run through them. And another one is pipeline parallelism, where this means that we split the models layers across multiple GPUs and we feed data through them like an assembly pipeline, like how we have an assembly pipeline of cars, how each person will start fixing each tire at each line and each designated station. That's how the parallelism runs here. And few other less common parallelisms are context and sequential parallelism, where in context parallelism, we'll be splitting long document into between GPUs and process it in different parts. And sequence parallelism is processing multiple short sequences at once by pipelining steps. One thing is like there have been many techniques where multiple parallelism strategies have been used while training the model. One of the example is in Llama paper where they had explained that they had used tensor pipeline and I think another parallelism according to their own setup, and they utilize it for training the model. And then the summary is like always we'll have to optimize for latency and throughput by using smart API selections. And if you're using APIs, having attention and KV caches in them can improve latency and reduces cost by a huge amount. And if you're doing your own inferencing, having building an own inference setup, that means that it's better to understand hardware-specific kernels and kernel optimization you can implement. I think that's all for my presentation.
Thanks so much for the wonderful presentation, Mia. I really like the visualizations of these different techniques.
Thank you. Thank you.
Very helpful for readers to understand and understand the differences between them.
Yes. Thank you.
Mm-hmm.
I think we can. And
yeah, so I guess what do you say is your biggest takeaway from this chapter?
Inference optimization is something very close. I like it a lot because at the end, like how how much the best model you have trained, but if you cannot bring it to the production and utilize it in a cost efficient way, it makes no sense. Like it becomes stale. Like the whole hard work of the huge researchers who build the model will go to stale. That's my
Mhm.
belief. And in this, it's a very nice approach where the author first go ahead with the starting, understanding what is GPUs, AI accelerators, how decoding part starts, and then they start. It's a very comprehensive approach where I have not even given, but she has explained and given a lot of pointers where how like each technique goes ahead, like especially with KV caching and quantizing. That's a huge research going on currently. Uh,
Mhm.
that's one big thing. And they talked about VLLMs, how inferencing, a lot of libraries have come up and they are trying to provide it. And then parallelization strategies, that's quite nice and very refreshing, where we understand like not just GDP, there are tensor parallelizing, how multiple parallelizing techniques can be matched and utilized. And even the author has given a better way saying that they are less common, but still these are also available. One basic thing is like last two techniques. Uh, for parallelization, contextual and sequential. Then again, one more thing we talk about is referencing, parallelizing, and this thing, inferencing with reference. Another thing is parallel decoding, which might be like very nice, but it's very difficult to be implemented. That's what they talk, especially with parallel decoding. But it has been used and people have tried to implement it and quite nice. And attention mechanism, actually, whatever I've heard and read about them, like they have tried to keep it as complete and as updated as possible. That's quite nice to go through. And yeah, anyone who is going through reading this, they they can understand to reduce their cost even using APIs, like understanding APIs, like what all is available, how you can use it to reduce your cost and bring your latencies. Quite nice. Very
Mhm.
thoughtful and very good one.
Yeah. Thanks so much for sharing. Sounds like you have
Thank you.
quite many takeaways from this chapter. So
Yeah,
hope
yeah.
you enjoy that, like fun reading and putting up the presentation. I think
Yes,
I
yes.
like the most about it provides some definition on the online and the batch
Yes,
of
yes.
inferences. So because it's actually a very common thing, like in traditional machine learning, and like when I was doing interviews, machine learning engineer, that would be a very common interview question people ask, like, what's the difference between batch and inference? And in your project experience, which one did you use? Yeah, I like that.
Yes,
It provides a distinguishing definition between for AI
yes,
and
yes.
traditional machine learning was some differences
Yeah,
there. And also, I
yeah.
think because my current work is it's more towards, I guess, the batch way because we pre-computed the response using LLM beforehand. I think that's
Mm-hmm.
also from what I see is becoming more and more common because if we have the data beforehand, we know what users want, and then having that pre-computed, and also we can apply more um, like solid and comprehensive testing, QA, and checking on these AI responses, which could lower a lot of the risk and uncertainties compared with the online inference. So I think
Yes,
that's
yes.
also a very interesting thing. But also there are also examples like chatbot or responding to the different users' requests. I feel like if it's serving more like a custom use case for each user, they might be different than maybe in B2C, like the example in the book, e-commerce, people ask what's
Yes.
the status of my order, things like that, and we need the online. But for B2B case, maybe if most of the use cases are pretty similar for basically we are serving to the same group of different user groups or roles, then essentially we know what their request and can sort of do the batch beforehand.
Hmm.
Yeah, so
Yeah,
I
very
think
true.
that's two like very two common ways people use that like in the industry.
Yeah, it's as I said, it's all about like how use cases, cost, and requirement, like how we can optimize all these things at a time. And here, LLMs is all about money, like how much you can get your bang for the buck with the processing and speed and output performance. But
Mm-hmm.
yeah, it's quite interesting and nice, and it's very nice where they don't talk only about less like inferencing part, where they talk with respect to aspect of API utilization as well. Like I think until I read this book, maybe I might have read but never observed where there are batch APIs available, uh, where you can utilize the batch APIs. It will take some time, but you will get it at a very cheaper rate. And some KV caching is available in APIs, which gives a very broader and thorough aspect of for anyone who is trying to be an AI engineer or even a higher enterprise or higher level managements where they understand these metrics are available and they can even utilize it whenever needed. Just like if you go with enterprises, you're reducing 10% cost might be millions for them. Like it's not a huge deal. That
Oh yeah,
makes
exactly.
sense.
I mean, a lot of teams essentially just work hard to increase a little bit of accuracy or reduce a
Yes,
little bit forces that
yes,
come
yes,
from machine learning models. So similarly for
yes, yes.
AI models as well.
Yes, like you can spend some few percent extra money cost and get a very high a very lower latency using KV caches or other techniques what they provide. And those are quite very amazing things and comprehensive approach, which comprehensive information which I could get out of this chapter, and it's quite nice.
Definitely. Yeah. And also I really think this area also has seen a lot of improvements. At least
Yes, yes,
from my experience using these models this year, I think in general they're pretty fast compared to with 2 years ago. Sometimes they will kind of get stuck for so basically the time to first token is super slow. Sometimes
yeah.
right now probably yeah, definitely I think these teams have done a lot of this optimization to improve that.
Yes, yes. People are more aware about low-level languages. I think before 2020 or something, people just wanted, before the LLMs came up, people were just creating models and trying to deploy. But once LLMs started coming and people started understanding like LLMs take a huge compute and the knowledge and understanding of CUDA, Triton, people have started adopting a lot and understanding, okay, why operating fusion is good, how to profile the models. I see a lot of people understanding and trying to work on it. Before it was just generating models. Now how to make models smaller, make it more faster, like VLLMs. Then we have llama.cpp. Those are all projects where they work quite hard and really amazing how they bring up multiple features and make it easier for people to use it. That's quite amazing to see
That's
that.
correct. Yeah. hmm Okay, I don't think we have other questions. So
Yeah.
thanks so much, Mia, for the presentation. And next week, we are going to talk about the last chapter in the book about the general AI architecture and how to collect user feedback. So looking forward to that chapter as well because that is has a lot of things related with system design, how to build a AI product that actually use can be beneficial to the users and by incorporating the users' feedback as well.
Yeah.
So looking forward to seeing everyone in that presentation. So,
Yeah.